Hi guys, my name is Isabella and this were my results for the extra credit assignment of the world's largest rope swing that we had to analyze. So this was my simplified drawing for the rope at the bottom of the swing. So as you can see, the rope is 150 feet long, but 20 of those feet are wrapped around the arc. Then the total height that from the top of the arc to the ground are 200 feet, and the jumper is 50 feet above the ground. So the mass I put was 75 kilograms, and then I assumed negligible air resistance, and that the rope was completely stretched. At the bottom of the swing. So for the first part, we had to say that the rope didn't stretch. So I used the energy principle, which says that the changing energy equals the work done by the surroundings. But since I took the system to be the person, the rope, and the earth, our surroundings do no work on the system, so it equals to zero. So our changing kinetic energy plus our changing gravitational potential energy equals zero. In this formula, all I had to do was plug in the values that I had and then solve for the velocity, which is 29.9 meters per second at the bottom of the swing, which is really fast. Then for the tension, I assumed that the net force equaled the force of the earth plus the tension force that the rope exerted. So the net force has a parallel and a perpendicular component. The parallel component is 0, and the perpendicular is just mv squared over r, which is the length of the rope. So all I had to do was solve for the tension force, and I got that it was 2,431 newtons. We still assuming that the rope doesn't stretch. I had to calculate the velocity when the jumper is 30 degrees from the bottom of the swing. So it was basically the same procedure as the first part, but all we had to do was include the cosine of 30 in many heights because the final height is different. As you can see, I used a little trigonometry, so what I got is that the final velocity is 28 meters per second, which makes sense because it's a little less than at the bottom of the swing, and that the tension force is 2,135 newtons. For the second part, we had to assume that the rope did stretch a little bit at the bottom of the swing. So what I did was, again, assume that the system was the person, the rope, and the earth, and the surroundings that do no work. I looked up some constant for the stretch, some Ks for the rope, which is really high since it's a rock climbing rope. And then I just used the energy principle, but this time I included the spring potential energy. As you can see in this formula, I had two values that we don't know: the final velocity and the final stretch. So I used another formula, which is that the force of the earth, mg, equals the force of the spring plus the perpendicular force. So I solved for v, plugged in the first formula, and got that the final stretch was a really small number, which is 10 times 10 to the negative 3 meters. And it's negative since our coordinate changes. Now, for the VPython animation, I got it to do something similar because I used the spring force code that we use in lab and change it a little bit so the motion is similar to the one on the video. So let me run it for you. So as you can see, it's really small, it's really slow, but it basically does what the jumper does in the video because he's not completely stretched all the time. He does like bounce a little bit in all directions, not just in the, so it's a 3D motion just as in the swing. So I hope you guys enjoyed it. Please click like,